I'm sorry for not being here earlier, but I'll give my talks in 2 days. And these will be talks about semantics. It's a cognitive approach to semantics, not really a linguistic one, but on the other hand, I will try to make it linguistic applications of this theory of semantics. So I will base most of my talks on this book, Geometry of Meaning, that appeared a couple of years ago. But I will also talk about some new stuff that I've been working on after the book. Before I start, I need to know a little bit about your background in order to adapt my examples for it. So, who of you have a background in computer science? You may raise your hand more than once. Who have a background in linguistics? That's good. Who have a psychology? Philosophy? Who think of themselves as a cognitive scientist? Okay, very good. Okay. Neuroscience, I forgot to ask about neuroscience. Okay, I will not talk very much about neuroscience, I'm afraid. I'm a cognitive science. I feel really like a cognitive scientist. But I will give things a little bit from, well, it will be talks in cognitive science. There will be very little pure psychology. There will be some philosophy, some linguistics, and a little bit of computational science. I will talk about, on the order from Lucas, I will talk about representation, I will talk about learning. When it comes to applications, I have two, I don't know how much time I will have to talk about applications, but I have two basic lines I can go. One is the direction of linguistics, the other one is direction of computer science, I mean computational implementations of semantics. Who would like to have the linguistic applications? You can decide later. Okay, who would like to have the computational applications? Okay, it's a mixed bag. Okay, we'll see what I do about it, but that will be at the end. So, that's the preliminaries. My motivation for these talks is a kind of an enigma here. Come on. So there is an enigma of language learning, and that is that we learn to understand words very quickly. When you finish high school, you understand about 60,000 words of your mother tongue. You don't use them, but you understand them. And that means if you calculate that, come on, yeah, you learn from the age of 2 to understand 8 to 10 words per day. And come on, very often we only need to hear a word once in order to grasp its meanings. So this doesn't work very well. Yeah. So the question is, how does this wonderful learning work? And we don't know very much about it. We don't have good models of that kind of quick learning of understanding words. And understanding words means basically understanding the underlying concept. Understanding a word means knowing its meaning, that is the semantic. I mean, I will talk about semantics of language. I will not say very much about grammar or syntax, but this will be a focus on understanding new words and how we can do it. And my take on this process is that words have structures that speed up learning. That's one component of it. And in particular, I will, in the middle of my talk, I will talk about why we have word classes. What is the cognitive reason for why we have word classes? That's one of the main points of my talk here. If you're a linguist, word classes are defined syntactically. I think that's a mistake. I think that word classes should be defined semantically. And that's what I want to give you here, a semantic theory of word classes. But before that, I will talk about concept representation in general. And by all means, please interrupt me at any stage. I mean, questions, comments, protests, applauses, whatever. I mean, any form of interaction is good. That makes the thing much more lively. So please interrupt me. So, before I get into my program, I want to talk about a little bit, very general terms about representations, the meaning of representation in cognitive sciences. And you can say that traditionally you can sort them into 3 groups. And the first one is the I need to stand here, I'm sorry, I don't like that. Is the what's called symbolism. That was the beginning of AI, of cognitive science. Everything was formulated in some formal language, ideally in logical formalism, then in computer programming languages. You try to describe everything in terms of some kind of symbolic representation. The second one is connectionism, neural networks, that somehow lives as a complement to the symbolic approach. But I want to advocate a third approach that I call conceptual spaces. That approach builds on spatial structures, having concepts represented in spaces, in some kind of geometric structures. And that's why I call my book The Geometry of Meaning, because I want this form of representation. So I want to spend most of my time talking about what I mean by these spatial representations. But let me say a few words about each of these three representations. So the first paradigm, this was with the beginning of cognitive science and AI in 1956. The computer was a new thing at that time. It was taken as a metaphor for cognition. The brain was thought of as being a Turing machine. So you had there was some kind of hidden program, and you gave it input, and then there was processing going on, and then there was some kind of output. That was the general metaphor. And the brain was seen as an information processing system in parallel to what was going on in the computers. And the idea was that there was a central processor. It was never found, by the way, but there was an assumption. And then there were memory systems. You had long-term memory, short-term memory, and so on. A lot of memory research was originated by this from this metaphor. But the underlying assumption is that there is a code that runs the system. And this code was then thought to be some kind of symbolic code, maybe not logic, but something closely related to logical representation. Yeah, and of course, the Turing machine is a symbol manipulator. So cognition was thought of manipulating symbols. That was the key idea of this aspect of representation. Now, if you sit down and try to feed information into a Turing machine, you need to have predicates or variables if you're a programmer. And one big question is, and then, yeah, these were the building blocks for describing information, and that was running the program, so to speak, the formulas. And then concepts was thought of. You built on this Aristotelian idea that a concept is given by necessary and sufficient conditions, and these conditions were then formulated in some kind of logical formalism. For those of you who know the computer language Prolog, it's basically built on this idea that you run concepts on necessary and sufficient conditions. But you still have to have the basic predicates. So here is a typical example. You define grandmother. Somebody is a grandmother if you're female, and there is a Y such that Y is, let's see now, Y is a child of X, and there is a Y and there is a Z, so that Y is a child of X and Z is a child of Y. That's what the meaning of grandmother is. I mean, this is a typical definition of giving necessary sufficient condition and given in logical formalism. But a major problem for this approach is, where do we get the predicates? Where do they come from? And the predicates are those symbols that are supposed to represent the concepts. Where do we get them from? Well, if you're doing things in this area, you as a programmer, or you as a semanticist, or you as a logician, or you as a linguist, had to feed in these things by yourself. And some approaches later, I mean, using connectionism and so on, try to circumvent this question. But that's a basic problem. And the second problem is, how can you learn the meaning of a predicate? I mean, you as a logician, you have to feed in these formulas or whatever, but yeah, you know the meaning before you do it. But we don't know meanings of concepts when we are born. We learn new concepts all the time. How do we do it? Well, I don't think we do it by necessary and sufficient conditions. There is a lot of empirical evidence that this method does not work. This is not how we learn new concepts. So, there was some progress using this, some applications, but in general, it's not, in my opinion, it's not a good model of human cognition. It's not a good model of human concept learning. Yes, very good.
So I'm not sure this is a fair way to represent the kind of traditional picture, right? Like first, no one thought the brain is computing, right? They think the mind is computing. Second, well, of course we don't learn the basic predicates by means of necessary and sufficient conditions, because they're the basic ones, so we have to have another theory. And there's a lot of work on how this could work. Like, so.
Give me an example of what you mean by how the basic predicates get into our minds.
Well, you know, like Fodor has this book on how this could work, so you have some kind of, you know, you establish some kind of relation to an external property, and this relation is, you know, like, mediated by some other representations, like, you know, maybe prototypes and some other stuff. So I'm just saying this it's not like maybe it's not not a fair representation of
No.
the
Of course, I'm a bit polemic here. I agree to that. But for your first thing, that it's not the brain that is doing the computation, it's the mind. That's a very deep and philosophical question that I don't want to talk about. It's your second one, you mentioned Fodor. And I think Fodor is the best example of this approach. I mean, saying that this is what gives semantics. But he has to assume that he assumes at least that the basic predicates are innate. And I think that approach has a lot of problems. I mean, first of all, we don't know what are the basic predicates. I mean, he never gives a good theory of exactly what are the basic predicates. And then I think it's a very strong assumption to say that all these predicates are innate. These would be my quick and immediate responses to Fodor's position. But yeah, okay, go on once more.
So first I wouldn't say that Fodor actually said this. I'm going to talk about this on Saturday, but what about like feature detectors, like some kind of like edge detectors, for example?
Now you're getting into edge detectors are normally done in non-symbolic systems. So then you get into another paradigm, and we can talk about that later. Of course, this has been complemented by other methods that can be used to generate basic predicates. That's okay. That's okay. That's what has been used in many systems.
Yeah, but this would be the answer.
Okay. Yeah, that's one answer, but it's not pure symbolism then. Okay. Yeah.
I just slightly different comment. I think you're also not completely fair to this approach. Fodor aside, I think, as far as I know, this approach is used mostly for the processing rather than for the learning approach. And I hope I agree that you put this aside, you will tell us about learning. But
Thank you. Yeah. So, no, it's used for. You're perfectly right. This is used for processing. But I still have this. That's why I started with this enigma. How do we learn the meanings of a word language? And this approach in my opinion, has problems explaining how we can learn a language so quickly.
But Fodor aside, it doesn't necessarily claim to explain it. That's all I wanted to say.
No, that's fine. That's fine. So, but I want to explain it. I mean, or at least have some direction, some answers in direction of it. So, okay, I'm unfair. That's okay. Let's go on because this is not what I really want to talk about. No, the other one, connectionism, and here you turn the metaphor around, and you start with the brain. I mean, these are neurons, and then you build an artificial system that is supposed to do the same thing with connections in different ways. Sorry, I have to put it here. Yeah. input and output of the neurons in the brain. You take the activities, the processing function of a neuron as a unit, and then you build complicated networks. So here are just two very well-known examples. This is a backpropagation network. I don't want to get into this description of how it works. This is a recurrent network. There are lots of different architectures. None of them really map onto what we know of the brain. They can be used to solve different problems. I mean, backpropagation is very often used to solve pattern recognition problems. This is the basis of what is now called deep learning. In deep learning, you have several layers of networks, and you have to train it and train it and train it. And recurrent networks are quite often used to analyze linguistic inputs, Elman networks, and so on. Yeah. You don't know what is given to you have some kind of perception system. They are the receptors, that's the input layer, to the system. You don't know what is represented in the system. There's a distributed representation. In the Turing machine, each memory unit keeps track of a particular memory. Here the memory is spread all over the system. One problem is that we don't really know what is represented, what is learned. I mean, you learn by training. You feed lots of input into the system, and then you slowly adjust these weights. And if you're lucky, the system can learn to classify your input. But it's very opaque what is really learned in most cases. And in general, learning is very slow because the adjustments of the connections must be done in a slow fashion, otherwise the learning breaks down. So you need to practice it on thousands and thousands of examples to learn something. And this is in contrast to human concept learning, which goes very quickly. So that's one reason I don't think this is a very good model of human learning. We can talk about applications later. But anyway, so this is connectionism. Now, my favorite paradigm. And that is concepts are modeled in topological geometrical structures. So spaces, basically. This is what I want to talk about. And I have introduced this notion of conceptual spaces. Information is organized in spatial structures. Here is the paradigm example, the color space. So this is a representation of human color perception. 3 dimensions. You have the color circle, red, blue, green, yellow. And then you have the intensity from gray to more and more intense colors. And then you have the brightness from white to black. These dimensions are not totally independent. When you get close to white, you can make fewer discriminations and so on. This is human color vision. Other animals have other color spaces. There are animals with 2 dimensions. There are animals with 4-dimensional color spaces. This is more an empirical fact, and this is established by having lots of people looking at similarities of colors and using methods like multidimensional scaling or something like that to extract the underlying spatial structure. There are variations of this model, but basically human color perception can be described in a 3-dimensional space. So this is one example. And then, of course, this is a perceptual model of our perception. Then we can discuss how this perceptual model shows itself in how language and concepts are constructed. But I'll get back to that in a few minutes. And the point here is that when I say that you judge similarities of colors, that means that if 2 points are close to one another, this point and that point are close to one another, that means that they are similar. So distances are inverse similarities in spaces here. The closer they are, the more similar to color perceptions are. Now, one problem I will not talk about today and tomorrow is where do these spatial structures come from? I mean, this is a basic problem for the theory of conceptual spaces. I will talk about that on Saturday in the workshop. I have some new ideas, but in the book I didn't write very much about this. But this is the topic of my workshop talk. Okay, so that's the third approach. So I'm just giving you these as a kind of background for what's been going on in the cognitive sciences when we are talking about concepts. The symbolic, the connectionist, and now the spatial. I will focus almost 100% on the spatial representation of concepts. But I want you to keep this contrast in mind, and please protest if you think that this doesn't solve the problems that I want them to solve. That's okay. Yeah, here comes a protest. I'm sorry, information?
The traditional picture can give you a really good picture, like good explanation of reasoning, of rational reasoning, right? Of like thinking. The connectionist models are really good at, like these kind of categorization.
Categorization, yeah.
What about
This
this?
is a model for how we learn concepts quickly. This is basically what I want to use. I mean, there are other uses, and I'll probably mention some of them. And I also want to show that this model can explain some linguistic structures, in particular why we have word classes. But that's, yeah.
But then, Peter, why don't you say this model is able to do both, categorization plus?
I'm sorry, yeah, thank you very much. It is also made for categorization, yes. And it's made for... I'll give you an example how we can learn much quicker using spatial structures than we can learn in connectionist systems. So it can help the problem of quick learning. But for me, that's the part of the concept learning, concept acquisition problem. But you're right. It can do categorization. Okay, now this is the background. Now I get into the main part of my presentation here. So I will talk about 6 different topics. The first one is, what is semantics? I mean, what do we want from a semantic theory? The second one is then to present my ideas of conceptual spaces, and in particular the idea of semantic domains. Third topic is how we can be sure that we mean the same things. I mean, I may have my meaning of a word and you may have your meaning of a word. How do we know that we talk about the same thing? This is the meeting of minds problems. Then this is the core of my talks, cognitive grounding of word classes. That will be what it's all leading up to, basically. As part of that, I will give you a cognitive theory of actions and events. That's in order to explain, for instance, how verbs work. People in these areas have not paid very much attention to how we learn verbs. And that's one thing I've been working on. And then finally, a little bit about how we can get compositionality of meanings from this approach. This is the menu. So, let's start. What is semantics? And I have put down a number of questions for that a semantic theory should be able to answer. Of course, I picked these questions myself, so I have some ideas about how to answer them, but still, let's go on. First question is, what kinds of things are meanings? And yeah, that's the first question. Second question, what is the relation between things we say and their meanings? I mean, how can we do this mapping between words and meanings? That's the basic idea of semantics. There is some connection between what we say and their meanings. Now, this is the learnability question. I've already mentioned it. You have to be able to learn the meanings of words. And then this is the how do we know that we talk about the same things question, the social question, that we share a language, we share an understanding of a language. How does that work? Very few people have actually worked on this problem. Yeah, I'll get back to that. And then, language is not a separate unit. I don't believe in the Chomskyan idea of language acquisition device, that language is separate from other cognitive processes. For me, language is something that goes together with other cognitive processes. So, I have this, what is the relation between perceptual processes and meaning? How can we talk about what we see, for instance? And then I have a particular focus on action. How can we talk about what we do? That's another. But there are actually lots of questions relating or other cognitive processes, perceptual memory processes to linguistic problems. So these are my questions, and I hope I will give some answers to all of them during these 4 hours. Okay? So, what are meanings? Well, basically, there are two traditions. If you look at the philosophy of semantics, there is what I call a realistic answer, and there is a conceptualistic answer. The realistic answer says that meanings are out in the world. The meaning of the word horse is the set of all horses in the world. That's an extensional definition. So meanings are out in the world. In the philosophical tradition, that's mainly associated with people like Frege and Tarski and so on. But it forms the basis of a lot of analytic philosophy. The conceptualistic theory says that meanings are in the head, that meanings are kind of cognitive structures. And I go for the conceptualistic theory, as you will. I will not be a realist here. Meanings are something that exists in our minds. So this is the basic division. And I'll get back to that in a second. Now, what is the relation between communicative acts and their meanings? Then we see lots of answers. In analytic philosophy, the focus has been on what's called truth-functional semantics. I mean, I already talked about this, realism versus conceptualism. But within philosophy, most of the truth-functional semantics built on realism. There are exceptions. There are people who try to be more pragmatic, people like Stolnacker and others who want to have a non-realistic interpretation of truth-functional semantics, but there are not very many. Basically, most of analytic philosophy has this truth function because truth relates to what's out there in the world. And this is, you can distinguish two flavors of truth-functional semantics. One is what is called extensional semantics. I mean, there is a language having words like horse or cat, and then there is the world. And so you define the meaning of horse in terms of what's out there in the world. You define the meaning of a sentence depending on how the world looks like, and so on. You give truth function conditions for these are the meanings. Then the second flavor is what's called intentional semantics. And it turns out that for many words it's not enough to talk about one word. You have to talk about several possible words, and then you get into possible word semantics. I don't want to talk about the details of this, but this is what's called intentional semantics. But still, semantics is thought of as a mapping between the language and a number of words now instead. And meanings are then given as truth conditions. This has been a driving force in a lot of analytic philosophy, to give the truth conditions for all kinds of concepts. So I gave you the examples of grandmother. That's a typical example of defining truth conditions for what is the meaning of somebody being a grandmother. Truth-functional semantics builds on realism. Cognitive semantics, which is a branch of cognitive linguistics, that builds on conceptualism. And then you have people like Lannecker, Lakoff, Tolmi, Herskovits, lots of people working in this area. And here is my take on that semantics is really this is the mind, and language is part of the mind, and semantics is a mapping between something, a linguistic structure, and something, a conceptual structure that you have in the mind. And then, of course, you have to somehow relate to the world, but that relation is not part of semantics. This is my idea here.
Can I ask?
Yeah, sure.
What is this relation then?
This relation is a relation of whether you succeed or not succeed. It's a question of pragmatics, of being able to communicate in order to jointly perform actions that give you success. So it's a kind of game theoretic approach to that. And I'll talk more about that tomorrow.
Reference would be part of pragmatics then?
No. Yes, in a sense. Reference would be coordination of meanings. So, I mean...
I can see your point.
Yeah. Well, I'll get back to it. I don't.
So I understand that the differences are really conceptual, but I'm wondering whether these two different approaches can be combined or used in the implementation. Are you going to talk a little bit about that?
If I have time, if I get to applications, I'll try to do it. But I will give you, when I get to this, how we can communicate, how we can share meanings. I will give you the answer to how I see to look at reference. It's very good that you say that they can be combined. Yes, they can be combined to some extent. I mean, we can take some ideas from traditional semantics and put them in here. But in general, I want to put focus on this. Yeah, okay, I didn't. Well, I should mention. I probably will do that soon. I should mention that within cognitive semantics, people have thought that these conceptual structures can be represented as image schemas. Some of you may, I mean, if you're in cognitive linguistics, you know what image schemas are. And that's a way of making more or less precise what is meant by the conceptual structures here. Yeah.
If I understood you correctly, you have said that meaning is independent of the word.
Just wait. I will get back to that. No. Meaning.
The answer is no.
Yeah. The answer is no. Yeah. But the answer is not at all in line with the traditional semantics. That there is a mapping from meanings to the world. I'll give you the answer in maybe not today, but yeah, today, later in the afternoon. I'll get to it. Yeah. Meaning is not independent of the world, but you'll see why. And then how can meanings be learned? And I will not say much about that because I will talk about that later today or maybe today, but maybe not in the morning. Let's see how far I get. Then we have the social one. And what is the relation between individual speakers and the communal language? And one of the more forceful criticisms against this conceptualist approach, it comes from the philosopher Putnam. And he has this famous quote saying that meanings ain't in the head. They can't be in the head. And he says that he can't distinguish a beech from an elm. These are two different kinds of trees. But he knows that there are people who can make this distinction. He doesn't, for him, the image schema of a beech and an elm or whatever, his concept of a beech and an elm are identical. I mean, they are just trees. He doesn't know very much about trees. But he knows that these two words have different meanings. So the meaning can't be, at least not in Putnam's head. There must be somewhere else. And Putnam uses this argument to say that meanings can't be in the heads, in the head of an individual. There must be some kind of realist complement to it. So you get that's his argument. I don't like his argument. I have an alternative answer to this enigma. So I'll get back to that. But I want to say that. Okay, this is the problem. Yeah. Okay. So how can we share mental representations? If everybody has their own meaning space, I mean, Putnam has his, I have mine, and you have yours. How can we know that we talk about something being the meaning of a word? We talk about meanings as they are unique. The meaning of the word horse and the meaning of the word elm and so on. Now, this is a new idea. No, it's not a new idea, but something that is not normally dealt with in cognitive semantics. That semantics is not just me and my head. It's also a product of me interacting with other people. And if I use a word in a particular way and you don't understand me, I have to adjust. We have to coordinate our meanings. And this coordination is what gives the meaning of a word. I'll give you a model of this in the afternoon today. So, meaning is a result, not only of what goes on in my head, but also what goes on in your head and our interactions. That's what's creating meaning. So it's an emergent phenomenon in a community of interacting people. And this is thing that is a little bit difficult to model, but I'll give you one model. So I talk about a meeting of minds as a basis for semantics. Now, this fact that we have to share meanings, that will actually put constraints on how meanings are constructed. So that will give constraints on how we create meanings. And I will give you an example of that later. So my way of modeling this is to use conceptual spaces. We all have our conceptual space, but then I'll use some ideas from game theory. That is coordination games. So this is my theory. Jose?
Well, you say, I agree with you that everybody has their own meaning space, and meanings are in a representation and so on. But then you have said, setting of meaning puts constraint on individual meaning. So perhaps we have individual meanings, but when you say setting of meaning, how meanings can be shared if they are individual? You know,
yeah.
I have my meaning,
and
you have yours, and she has hers.
Yeah.
How setting of meaning takes place? It's not something that you can put, oh, I think so, and I don't know, you can put in a paper and say, oh, this is my meaning, look at it.
Yeah.
So I would like a clarification on that.
Yes, I will. But you have to wait until the afternoon, because then I will give you the model. So it's a very good question. I mean, it's a very serious problem. Actually, it's a serious problem for cognitive semantics to answer this question. I'm not saying I'm giving you a full answer, but I'll give you some model of it. And that model will be based on this conceptual spaces plus game theory. So, very simplistic picture. You have two individuals here. One individual with a conceptual structure, another one. And you have to somehow get a, this is what I call the meeting of minds. These meanings must be coordinated. And then exactly how this coordination is done, I will talk about in the afternoon. It's not sure that my perception of red is the same as your perception of red. This is a famous phenomenon of qualia in philosophy. But somehow we are able to coordinate our perception somehow within language. Okay. So my answer to Putnam's question is to say that meanings are in the heads. You need a community of speakers in order to determine the meaning of a language, or meaning of different words. Now, final questions, the cognitive ones, relations between perceptual processes and meaning. So a basic question is, how can we talk about what we see? And the brain doesn't only use linguistic representations of meanings. We have representations of vision, of sound, and language and music. We have different, I don't want to really use the word code, but somehow we have different modalities of representation in our brain. And the question is, how can we coordinate these codes? And this is a very basic problem. Any child who can speak can see a picture and start talking about what's on the picture. You can take a visual input and you can describe your visual input. This is a fantastic process. We don't know how we do it. And conversely, any child who hears a story, bedtime story or whatever, can sit down and draw some kind of picture of what goes on in the story. You can take what you hear and turn it into a visual phenomenon. We can do this translation between vision and language, and we know very little about how it's done, but it's really a fascinating problem. Yeah, this is what I said. Now I get to the image schemas. This is the relation between perception and meaning. So people like, as I said, Lanacre and Mark Johnson in philosophy, Lakoff and others have been working on this. Here's one example from Lanacre. So this is how he represents the verb to climb. So there is this basic time dimension. You have a process. Climbing is a process. And you have three different frames for what's going on here. There is a vertical landmark. This is the LM. And there is a trajectory. That's the thing doing the climbing. And then you have a process that means that this trajectory is in contact with the landmark and it's moving moving upwards along the trajectory. That's the basic image schema for what's going on in climbing. Then you can turn it into an image schema for the word climber. And climber means that now you're focusing on the trajectory here, the person doing the climbing. Now here these thick lines means that you have your focus is there, and here in the verb the focus is on the temporal dimension. Here the focus is on the thing. It's turned from a process into an object, but basically it's the same structure. It's a matter of shifting your attention from the process to the object doing it. And that's the difference between the climb and the climber. This is a typical example from how people in cognitive linguistics treat meanings of words. And Lakoff and other people are doing, Talmy, Haskowitz, lots of people are doing similar things with other words here. Yeah, it relates to Gestalt psychology. I don't really want to get into the details here, but they have a lot of influence on that. The second question, relation between action and process. Lots of people, I should say, very few people have been working on this problem. So verbs normally express either actions or results of actions, and I will get back to that tomorrow when I talk about the verbs. And now, my take on this is that this is a picture from Marr's book no, it's not from Marr's book. It's a later article with Weiner, how to represent actions. So they look at, they have small differential equations here. They look at the patterns of movement here. They do it in terms of patterns of movement. I think, and I will try to give you arguments for that, it's better to look at the patterns of forces. So when you're doing things, you're performing certain force patterns. So my idea, that I will explain later, is that actions can be described as force patterns. But I'll get back to that. So this brings in the force domains here. Some people in cognitive linguistics, in particular, Talmy, has been working with force dynamics as part of the image schema. So if you know Talmy's work, you know what I mean here. So that's the end of the first topic. What is semantics? I'm not sure I will be finished with the second topic this hour, but let me start. Okay. Yeah, go ahead.
Time for questions?
Yeah, sure.
Just a couple of small ones I'd like to speak with you, or maybe you'll address them later. I think you're being very optimistic when you say kids really learn and understand 8 to 10 words. Yes, it's true in a sense, but they don't really know the meanings. So you know Sue Carey's famous experiment with chromium, right? The tray experiment by exclusion. The kid learned the meaning, but only by saying this new word means what the other doesn't know. So I think it takes, and I hope you could talk about this later on, but it takes a lot more time to actually narrow down the meaning.
Yes.
So I just want to say you're a little over-optimistic.
Yeah. No, you're perfectly right. And I'm not saying that a child learns the full meaning of a word in one shot. Yeah. No. Yeah, I didn't say it, so you didn't misunderstand me. So, yeah, that's perfect. Yeah.
And the second thing is...
But can I just stop you here?
Please.
This means that there is not talking about the meaning of a word may not be a very well-defined concept. Meanings develop as we learn more. So, about the concept. But still, a child is able to grasp the basic components of the meaning. And I'll tell you in a while what I mean by the basic components of the meaning of a word very quickly. Then the meanings develop.
Then they overgeneralize.
Yeah. Exactly.
Right,
Yeah.
And the second thing, maybe again you're going to say something about this, but I'm saying this partly also for the audience because I know there's some linguists. Do you really, you said quite strongly that you don't want to make a linguistic classification to verb meanings, but clearly people like Bess Levine have shown that the syntax, if that's what you mean by linguistics, is indeed very strongly related to the semantics. And again, in acquisition in children, like Pinker has shown in his thesis, for example, children or Lila Gleitberg have shown that, the semantics come out of the syntax and vice versa.
Yeah.
So I'm not sure it's, you can really make a very strong argument for saying, I don't want linguistics in the semantics of acquisition of verbs.
I want actually very little. I mean, okay, let me make a confession. It's not explicit here, but it's implicit. I want to develop a syntax-free semantics. I'm not sure I can succeed. I will get back to syntax if I have time for the applications at the end. But this is actually one of my goals, to have a syntax-free semantics. Now, I'm aware of the things you're mentioning here. And of course, I'm already contradicting myself a little bit, because I'm saying that I want to have a semantic characterization of word classes. Now, you recognize a word class by their syntactic components. For many languages, you can see whether a word is a verb or a noun or an adjective by the syntactic marking. And that gives you a clue to what is the meaning of the word, because you know what kind of category it's referring to. So in that sense, my theory is not perfectly syntax-free. But I only use syntax as a kind of marker to understand what kind of word we are dealing with when we are learning new words.
But beyond that, so for example, English-speaking kids overgeneralize the rule that nouns can become verbs.
Yes, yes.
The kids will say, I broom the floor.
Yes, yes.
Which is completely logical.
Yeah,
This
yeah.
happens not to be a gap, right?
Yeah.
So that shows that they have acquired a rule that crosses part of speech
Yeah.
and also syntax.
Yeah. Let's save this. I like these examples, but let's save them until I get to the verbs. Yep.
So isn't the beautiful thing about language that you can somehow communicate, somehow have really good conversations, despite us having very different beliefs about what we're talking about, right?
Yeah.
We have very different meanings, and still we can talk about the same things. We can somehow get a conversation going, right?
Yeah.
Now you're saying, well, in order to communicate, you really have to have the same meanings. Plus you're saying the meanings are somehow something that is emerging from those two meanings.
Yeah.
If we have a conversation. So I'm not sure if you maybe already rule out like what's the most interesting about language, or maybe, at least a very interesting thing about language, that we somehow manage to talk about stuff despite having very different experiences, and despite having very different meanings.
Yeah. No, you're perfectly right, and in particular, we can have very interesting conversations about fictional things. I mean, you can have serious debates about Star Wars, or about unicorns, or about witches. Peter Gärdenfors has this famous paper on intentional identity. We talk about Hob and Nob talk about the witch, and I think they mean the same thing. But of course, the witch doesn't exist. So how do we know they're talking about the same thing? We don't know it, but we can still have wonderful conversations about witches and unicorns and other fictional things, because to some extent we have some form of alignment of the concepts in our heads. The alignment is not perfect because there is no reality hitting back in these cases. So I hope I can give you a partial answer to how we can do it in my account. Yeah.
It's like a social interaction, you come together and kind of create these terms.
Yes, yes. Yeah, yeah. And it's...
When we separate that kind of...
Yeah. I mean, unicorn is created because we know what the horse is and we know what the horn is. And we can just put the horn on a horse and then we get the unicorn. We have the meaning components, so to speak. And that allows us to talk about unicorns. Yeah.
In your talk, first talking about connectionism, you said that connectionism is about like slow learning, which is like opposite to the human learning, which is quicker. Maybe like first language learning is quicker, but connectionism doesn't like simulate the second language learning or third language learning. Okay, this is like my first comment. My second one is about Chomskyan, view of mind, and they said like language is a separate model of the other cognitive models. But you talked about different codes, so like pretty much the same. We have the language as a code, but they're not separate codes, maybe not modular point of view, but those codes are in Chomskyan terms. Those modules can be like interactive between each other. So we have modules, as you mentioned, codes, but they can be interactive. They can interact in a way or another. Actually, my third third one is talking about meeting of minds. It's true that when we talk, I can have different meaning and you have a different meaning, but we can reach like a mutual understanding through like a well-known social linguistic concept, which is accommodation.
Okay. Yeah. First question: connectionism as a model of second language learning. No, I don't think it works, but I'm not sure I can give you a detailed argument. Second question. Come on now. Chomsky, sorry. Yeah, no, of course. We have words and we have syntax. I will not talk about syntax. Chomsky thinks that, Chomsky doesn't really have a theory of words. He takes them as units and they're given somehow. He talks about phonology, but that has nothing to do with semantics. He talks about how you put words together. I will say a little bit about how you put words together at the end of my talk here. But in general, I'm not very much interested in this syntactic structure. So when he talks about code, he mainly talks about the syntactic structure. That's the title of his book. But I'm talking about the mapping between words and meanings. This is the kind. So words for me is a form of code, yes. But I haven't developed any theory of syntax that would match what Chomsky is doing. So there is a bit of mismatch between our programs. Meeting of minds. Accommodation is a word I have problems with because I want a model of accommodation, and I don't really see any good models of that. There are people, Pickering, Garrett, and so on, who do some. They call it alignment instead, which is similar. Still, not a very good model of alignment. So, and I don't have a really good model either. But next in the afternoon, I'll say a bit more about how what I mean by this meeting of minds. Okay, can I spend 2 minutes on conceptual spaces? By the way, thank you for the questions. That means I will not save any special time for questions at the end, unless you want. Any more questions now? Yeah, okay, go ahead.
You still have 9 minutes.
I have 9 minutes. Okay, we started late, you mean? Okay, good. Yeah.
Go ahead.
Okay, just because you spent time on it. A few slides ago, we were talking about action, language, and meaning. You talked about this mapping between people listening to a bedtime story and being able to create pictures. Just that works with visual and spatial concepts, but you also grasping that with music and whatnot. I'm intrigued about the phenomena, just if you could specify the kind of phenomena we're talking about. So it's clear in the case of stories and pictures, but less clear for me in the case of music. You can get onto this maybe another day, so shall I wait?
No, that's fine. I like your example here because we have developed, language is very good at talking about what we see. Yeah. Language is not very good about talking about what we hear. In particular, if we come to music, it's very difficult to give a description of a musical piece in language. It's very bad at that. We are not very good at talking about what we see. I can recognize a face after seeing it once, but it's very difficult to give a verbal description of a face. People try, but it's very difficult. So for spatial relations, we have a very good language. For faces, we have a bad language. So that means that language is good at certain perceptual phenomena, but not at others. And that's a very interesting point. What perceptual phenomena do we have linguistic tools for? And I know some, but I don't know, and I don't have an answer to the general question. Yeah.
Just a follow-up question before this. So, do you think that there is a kind of a space that language works very well in? Because of course, you could make the argument that cross-cultural diversity tells you something about different solutions, for instance, to spatial language, to the spatial reference problem. Do you think that there is some sort of tendency or something that you can identify that will tell you something about the language?
Spatial language works very good for relations, spatial relations, not for more precise, like describing the structure of a face. The general answer, I think, to the question of what can we talk about, what can we use language for, is would be an evolutionary one. What do we need language for? What kind of things do we need to communicate about? We don't need we don't need to have a description of how a voice sounds or how a musical piece sounds. We can share it, but we don't need to describe it. We need language. I mean, I have a theory of the evolution of language, which I will not talk about, but we need to coordinate things. We coordinate actions. That's basically. And describing spatial relations is very important for coordinating actions. So that's why we can talk about it. This would be a very brief outline of my answer to that question, but I haven't developed it. So. Yep.
Yeah, just a very short follow-up to your last answer. I'm not sure if I understood that correctly, but if you meant that language, or like spatial perception, is inherently different from auditorial perception, and therefore it is easier to describe spatial relations than something like music, I think I would disagree, because of course there are musicians which can very precisely hear what music would sound like by just getting it right. So it's just a thing of exposure, I guess. Because it's exposed to the spatial relations today, but
very good. Now, the word you used here, musicians can hear music by having it described. Described means that you see the score of a piece, and a skilled musician can hear the music just looking at the score, just as we can read the text and so on. But that score is then, I wouldn't say it's language. It's a different representation. It's a representation of the pitch and the duration of tones and so on, and how they go together in harmonies. It's a different representation, but it's not. I wouldn't call it a linguistic representation. No. You can talk about single elements of the music, but you can't describe the Ninth Symphony of Beethoven or whoever in words. Wittgenstein said you can whistle it, but that's a different code. No, I don't. I think actually language is very bad for describing language as such as describing music. Okay. Thank you. Now I have 5 minutes, so then I'll now I don't want to have any more questions at the moment. So, Conceptual Spaces. This is my previous book. I already said something about the topological geometrical structures, but I will use the notion of a dimension. And dimensions here are color, size, shape, weight, position. I have an open list of dimensions. I'll give you examples later. So here is two very simple examples of dimensions. Time dimension we think of in Western cultures as a real line. There is a designated point that is now, then there is the future, which in most, metaphorically in most Western cultures mean going to the right, and it's in front of us, and there is a past which is behind us. Some cultures change the ordering of this, but that's another story. Now compare this with the weight dimension. The weight dimension is only half a real line. It's only positive numbers. We don't talk about negative weights. So the dimensions here have a different topological structure. One has an endpoint, the other one doesn't have an endpoint. So there's very trivial examples of different structures here. And I already mentioned the color space. Dimensions are sorted into domains. So the color space has 3 dimensions, size has 1, weight has 1, position has 3, shape we don't know about what it is. We don't know very much how we recognize shapes, but we are very good at it. And that already says this, that less distance in a space means greater similarity of meaning. Now, here comes my idea of concepts of represented and convex regions. This is for me a kind of theory that can be empirically tested, and Jose has protested against my idea here, but let's not take that Convex means, let me do an example here. Here's the color space again. So we have these perceptual dimensions. And convexity means that the concepts that we form, the color concepts that we form, like the concept of red, means that the definition of convexity is that if this point is called red and that point is called red, then anything in between is also called red. So the notion of betweenness here. If something falls under a concept, another thing falls under a concept, then anything in between also falls under the concept. That's the definition of convexity. And that means that there will be no base in the shapes here. I don't want to get into the mathematics here, but that's the basic meaning of convexity. So in my talk, I will use these concepts, the notion of a domain and the notion of convexity, quite frequently. So why do I want to have convexity? Why is this a good notion? And by the way, note that this notion of betweenness, that's a very fundamental geometric notion. I mean, that forms, it's not the only geometric concept, but in symbolic codes, in logic and so on, it's very difficult to describe betweenness. But if you have a spatial structure, betweenness comes for free. And then you can define a convexity. You can define betweenness in connectionist system as well, but it's less clear there. It connects to prototype theory. I mean, this is one example where I connect to psychological theories of concepts. So let's take an example. Assume that you have a two-dimensional space. The argument works for any dimension, so it doesn't matter, but I can draw two dimensions here. This is a two-dimensional space. And you have prototypes here. You have prototypical colors, or you have prototypical birds, or you have prototypical fruits, or whatever studied in prototype. And let me have one more minute to finish this argument. So these are the locations of the prototypes. Now, given the prototypes, you can have a very simple rule of generalization, say that if you see a new thing, this is a new observation you make, it has these two values of the two dimensions, then you classify it with the closest prototype, the most similar prototype. So any new thing is sorted with the closest prototype. Now I use the word closest, and that means I'm assuming there is a metric, which is a bit stronger than just assuming betweenness. So if you have a metric space, then you can talk about the closest prototype. And this simple rule gives rise to what is called a Voronoi tessellation. It's a Russian mathematician. And the Voronoi tessellation means that this line is the line that divides the midline between P1 and P2. This line is the midline between P2 and P3, and so on. You can see the middle lines here. And if you draw all these middle lines, you end up with areas like this, regions. And it's a two-line mathematical proof to show that these regions are always convex. So if you have prototypes, if you have a metric space, and if you do this classification, always sort an object by the closest prototype, then you end up with a convex categorization of a space. But I mean, it builds on these assumptions of metric space. Now I stop. I mean, I'm in the middle of the presentation of conceptual spaces, but we will continue in the afternoon. A quick question.
I was just wondering how you sort of, it seems like to do this, you have to ensure that the prototypes you're looking at are sort of in the same, I imagine sort of the conceptual hierarchy, they have to be in the same sort of level.
Yes. Yeah, I mean, if you go by Eleanor's theory, you have the basic level, you have subordinate and super. I'm assuming that all the prototypes are on the same level. Yes, you're perfectly right. So, thanks for today, or for the morning, and we'll see you again in the afternoon.